Ladies and gentlemen, once and dear lovely students, a very warm welcome to the session today. First, I would like to take this honor to introduce George Sir to all of us. Uh, Please join me in welcoming Mr. George Salazar, an esteemed scientist with an illustrious career at NASA. Sir has spent almost 40 years at NASA working on different missions and has led various teams across the different verticals. Sir has been instrumental in pioneering numerous space missions and technological advancements that have not only expanded our understanding of the cosmos, but also significantly contributed to our everyday lives here on Earth. Today, in this session, we are going to discuss about space flight development opportunities and what NASA is working particularly from George Sir himself. With a big round of applause from everyone's side and a very warm welcome once again, George Sir, on the platform and encouraging all of us to continuously be inspired for sciences. Over to you, sir.
All right, thank you very much. Arpit. Pleasure to be with you all this morning. Well, morning here, afternoon over there. So let me get the presentation going here.
Sir, you went on mute.
Okay, can you hear me okay?
Yes, very well, sir.
Okay, great. And can you see the presentation?
Absolutely, sir. Clear.
Excellent. All right. Well, good afternoon over there. Good morning over here in Houston. Actually, I'm in San Antonio, which is not too far from Houston. Again, thanks for inviting me to speak to you all. And what I want to be talking about in my presentation today, and I'm going to keep it at a very high level. All this stuff can get into a lot of the detail, but I just want to share with you kind of a high level view of science and engineering needs for spaceflight development. And of course, there'll be hopefully some time for questions in case there's something that you want to ask me. So let's see here. All right, so here's what I'm going to be talking about. First of all, I'm going to talk about the interrelationship between science, technology, engineering, and the human. Sometimes we don't hear about the human a lot. All we talk about is science and technology and engineering, but human actually is a very important element in system design. And that's something that NASA takes very seriously. And I was in the last my 5-10 years working at NASA, I did a lot of study about the human, how humans behave. So anyway, I'll share a little bit about that in my presentation. I'm going to talk about science contributions to spaceflight. And, science has its place in spaceflight. And, some of the things that have occurred in science have contributed to human spaceflight, especially going to the moon and even going to other planets as well. So I'll mention that. And then human spaceflight challenges, there's a lot of challenges for humans to go to other planets. And I'll just share a few with you. And then addressing the challenges through the sound systems engineering process. And basically what I'm going to be talking about there is kind of like a method, if you will, of how NASA develops complex systems. NASA doesn't develop something like the space shuttle, they say, well, let's just put this all together and hope it works. It's not the way we develop systems. We have to think about it in a methodical, very meticulous way of developing a system. And I'll share that with you and some closing remarks. So here's kind of a picture. Let's call it the gears, the inner working gears of basically four things. First of all, science. You hear about scientists and of course scientists, excuse me, they seek to understand and discover things that we don't know quite well, whether it's the weather or how a planet atmosphere is and things of that sort. And then, of course, the foundational laws like gravity. For example, technology, it builds on innovation, and these are the physical things: computers, televisions, iPhones. That's technology, and these are products, physical products that are used by engineering, which is cost cut. It's a cross cutting. Engineering includes the science and technology to solve a problem. So that's what these gears basically show. And then I show about the human. Okay, the human is part of a system. Okay, and so we have certain limitations and capabilities, and so that's part of the system development. And that's something that became very obvious to me later in my career, because originally I used to just study, the computer systems and the software, but never thought about the human using the system. And you can have a perfect design system made up of computers and software, but if the human doesn't know how to operate it properly, the whole system fails entirely. And so that became very important as part of human systems, what's called human systems integration. And I'll mention a few words about later in my presentation. Okay, so space exploration includes astronomers, uncrewed probes, and crewed spacecraft. We have, like, for example, the Hubble Space Telescope, James Webb Telescope. We have navigation. There's a picture right up here of a what they call a star tracker. That's kind of like somewhat of a GPS, so to speak, for spacecraft. Looking at the stars, they can figure out where they're located relative to the star's position at a certain date and a certain time. So the whole aspect of navigation for either a crew mission or uncrewed mission is very dependent on this kind of technology that science originally looked at, and with the help of engineers, developed things like, for example, the star tracker. Digital photography, the astronomers wanted high resolution pictures. And so with working with engineers, they came up with better ways of capturing good pictures of the stars and the galaxy. Computer technology became very explosive because of supporting a lot of this astronomical observations of stars and all that. And that computer technology went over, to human spaceflight as well. So computer technology has been a big one. Remote sensing, we have that right now on Earth, where we have satellites looking at, for example, the hurricanes that form in the Atlantic or the Pacific, the temperatures, the ozone layer, carbon dioxide, all these things related to remote sensing went over into the space exploration, because a lot of the satellites, for example, the orbiting satellites right now that's orbiting Mars right now, including one by India, are using remote sensing technology to look at the Mars atmosphere and try to understand a lot of things about the Mars atmosphere. Like, for example, hopefully one day we'll find out why the Mars atmosphere pretty much was lost. At one time, it used to have an atmosphere. At one time, it had water. And what happened to it? Why did it disappear? That's some of the things that we need to understand, because it could affect the way Earth one day may experience that. And so, again, with science, and engineering and technology working together to look at these kind of problems. The contributions to spaceflight is not just ground observations, but also what we call physical observations. And so ground observations is, for example, possible landing sites. During the Apollo spacecraft missions back in the 60s, we used observatories, to look at possible landing sites on Apollo. Right now, for the Artemis program, and I'll say a few words later, is the current Return to the Moon program that NASA has been working on. And I worked on it the last 5 years, actually last 10 years of my career working the Artemis program, starting with the Orion spacecraft and then working the human lander system. And then, we're looking at future landing sites, like, for example, the Saturn moons. Some of the Saturn moons have water. So if there's water, is there a possibility of life? And that's the exciting part about space exploration and leveraging science and leveraging technology and leveraging engineering, to come up with a possibility of a system that can go to Saturn and see if we can find life there. And then the physical observations is related to robotics, robots going before humans landing. Mars, the moon surveyors, like, for example, here's a picture of the lunar surveyor that was used before even humans went to the moon. And so, the robotics precursor kind of gives let's say, a scouting, if you will, looking ahead what the astronauts may experience. Right now on Mars, you can see a picture of the Mars Perseverance robotic system, along with its little partner, the Ingenuity helicopter. Unfortunately, the Ingenuity helicopter experienced a broken propeller wing, and it's no longer able to fly. But it gathered a lot of information, and in fact, that particular design and the study of how to fly a helicopter on another planet is contributing to a probe called Dragonfly that's going to be flying around one of the moons of Saturn. So again, you have the science understanding, where we're going on another planet, and then the technology of like, for example, observations such as telescopes, and then also robotic systems, that basically has science experiments to land on another planet and see if there's, like, for example, water. Can we convert an atmosphere there into something that's usable for humans to live and work on another planet? So again, it's always the science, the technology, the engineering, and the human aspect all working together to understand better space exploration and help us answer questions that we have about our solar system and our universe. So there's human spaceflight challenges. Ground and robotic exploration provides limited knowledge. There to the right, you can see the spectrum of hydrogen, helium, oxygen, neon, and iron, and other elements that have a certain spectral characteristics. And using technology and science, we can figure out what's the other composition of a planet made up of, what kind of oxygen, or what's the atmosphere made out of, and what's the ground made out of, and things of that sort. So we can do that to a certain extent, but it's really the next step is humans actually taking humans to another world and use the creativity capability of the human, the adaptation of learning how to operate systems, learning how to ask questions, and learning how to take what they have with them and create new ways of exploring the planet. But we got to define the mission. We got to develop a concept of operations. In other words, how we're going to operate in another planet. Something called requirements. Requirements basically says, what do we want this system to do? That's very important in engineering. And then develop the systems to accomplish the mission. I have to say that future space missions are going to grow in complexity, just simply because the technology is growing. And so that gives us capabilities of asking more, gathering more data, and answering some questions that we have been lingering on for a long period of time. Understanding the system in a mission requires, how are we going to use this system in the real world, and what's the environment? What's it look like that this system's going to look at, and what's the technology that's needed? And what's the role of the human? Will the human be part of that system? or maybe just make observations, or will he or she actually be operating these systems? And there's a picture here that's taken from a handbook that I helped develop called Human Systems Integration Handbook. And it talks about the human, the software, the hardware, and then the environment. But also, what's the mission? Okay, all these operate with a certain mission in a certain environment. And that's part of the science, technology, and engineering in developing the tools needed for a certain mission. Complex systems require a very sound approach. We call it tactical approach, is to decompose it into management pieces. You know, over here to the right, you can see the pieces that make up a car. And, you know, you wouldn't think about all the pieces involved with a car, but you have to think also each one of these pieces interact with another piece, and they have to fit perfectly and they have to operate perfectly. So you think about just a car, the complexity of a car. Now think about a complex spacecraft going to another planet. The amount of pieces are incredible. And so, you know, we have certain ways of doing that. There's something called model-based systems engineering that is basically can take a large system and decompose it into small pieces. And that's the important thing about the engineering process, is you can take a complex system that's made up of many different subsystems and take that subsystem and look at it and break it down from a very difficult complex system to something that's maybe a little difficult, but then now take one of those components, and such as a flight computer, and have a better understanding of each subcomponent. And then so understanding all the different pieces in when we break it down to smaller pieces will help us view the entire system as a whole. So the whole important point of this is to break a complex problem down into smaller pieces. All right, so Artemis mission, I mentioned this earlier. So this is our return to the moon mission. They call it the campaign because there's going to be different pieces, different projects rather, and programs involved in returning to the moon. You know, we're going to have first of all, we're going to have the Orion spacecraft sometime later this year. Going to take 4 astronauts around the moon, and then we're going to start build a orbiting. We call it a moon orbiting station, which will be continuously orbiting around the moon. And then we're going to have visitors. Let's say the Orion spacecraft, the Human Lander System that's being developed by SpaceX, to dock with this orbiting space station, very similar to the one we have currently right now orbiting around the Earth. And then gradually we're going to be building capability. And then as we're building capability orbiting the moon, we're also building capability down on the surface of the ground of the moon. You know, we're going to be building lunar rovers. We're going to be building habitats, for housing astronauts. And we're going to be building better spacesuits so the astronauts can live and work on the moon for a long period of time. All this is a dress rehearsal for eventually going to Mars. But we cannot go to Mars, especially with humans, until we know the technology is ready. It's just simply because if they have problems on Mars, it's going to be a long time before they get help in case they're in trouble. The moon, it's only 2 or 3 days away. So if they're in trouble on the moon, there's a high likelihood that we can rescue them. But going to Mars, it's a different story because of the distance. And so we got to prove out all this technology before we go to Mars. And that's one of the main reasons for the Artemis mission campaign. It's going to be an increase in mission complexity, no doubt about it. Hopefully many of you kids out there are going to get involved with it. ISRO is very much involved with the Artemis program, as well as other countries. So let me just talk about the human needs in space. And what you're seeing here is the human and things that affect the human related to space exploration. First of all, gravity, the physiological changes, like for example, your bone, you lose bone mass, your fluids in your head don't drain properly. They stay in your head, and it makes it look like you have a swollen head, just simply because of the fluids not being drained by gravity as here on Earth. And so, with the combination of exercise equipment, training, and medication development, we can overcome this. And these are some of the big challenges related to altered gravity. Space radiation is a big problem going to other planets. You know, one of the reasons why uh, right now the orbiting space station can fly astronauts for a long period of time is because the Earth's magnetic field protects to a large extent the astronauts in terms of space radiation. But once we start moving away outside of that protective dome of magnetic field, we're going to have to depend on technology and medications to prevent cancer and something called CNS, cognitive neurological system disorder. Basically, it says as you get into space longer periods of time, that space radiation affects your ability to think. And so that's not good for an astronaut because an astronaut is operating complex systems, and we want to make sure that they are at their peak in terms of thinking. Isolation and confinement, they're going to be away from their loved ones, and so how do we deal with that? How do we deal with being away from their wives and moms and dads and children for a long period of time, and also as the sun moves further and further away from these astronauts, their what we call their sleep ability to sleep properly gets disrupted. And so, how do we deal with that? Well, we have to develop lighting systems, using science, technology, engineering to come up with artificial lighting to kind of get around all that. And then we're going to have a hostile closed environment. Mars and Moon were not meant for humans, okay? And so there's no food on Mars. There's no food on the Moon. We're going to have to develop our own food. We're going to have to develop our own water. We're going to have to develop, let's call them habitats or little living quarters, if you will, to protect the astronauts. And of course, oxygen for them to breathe. We depend on oxygen to breathe, and there is no oxygen on the Moon, and very little on Mars. And in fact, what little atmosphere there is on Mars is not really breathable. So we have to come up with ways of overcoming that. And then the distance from Earth, emergency. Let's call it the emergency medical room. That's space ready, that's designed for the space environment, and the medications needed in case the astronauts, get sick or they have, let's say, heaven forbid, one has a heart attack or a blood clot in their brain. How are we going to deal with that being so far away? And that's part of also the science, technology, and engineering, along with the human, to try to answer those kind of questions. And then I'm just going to go briefly through some of the technology that's needed, and obviously we need power. We got power in cities, to power all the houses. We're going to have a lot of power to power everything on the Moon and everything on Mars, and so power is going to be very important. Robots, we need robots, to take care of some of the more dangerous parts of a mission, as opposed to sending humans outside of a habitat or outside of a spacecraft. So robotic systems are a big need in terms of future space missions. Because of the radiation effect, we have to develop computer systems, and there you see a computer card that's designed for what we call heavy space radiation effects. And then, of course, the human is going to be vital for these missions. And the human interface, the picture there shows the human with let's call it the machine, interacting. That was something that I was involved with. What we call human-computer interfaces is develop a human-computer interface that can handle, potentially problems that the astronaut may hit the wrong switch or activate the wrong function. And so we have to prevent that. And that's part of the human computer interface. And that's why I mentioned earlier that the human has certain limitations and capabilities. And so understanding that, we can design systems, to prevent problems. Habitat, as I mentioned earlier, is going to be important. They want a safe place, and of course, you all, want to go home and, have a nice bed, nice place to sleep at night, roof over your head so you don't get rain on you and things of that sort. Same thing for astronauts. And of course, right here is a picture of communications between Earth, Mars, and Moon. And it's going to be very demanding in terms of developing, call it the Internet of Space, for all these activities that we plan to do in other worlds. And then how are we going to land these massive spaceships on another planet? There's something called kinetic energy, which there's a formula for it: 1/2 times the mass times the velocity squared. And so a large object going at a very fast speed has a lot of kinetic energy. How can we slow something that big down to where it can land on, like, for example, Mars? If you cannot slow it down properly, it's going to go beyond Mars and on out into outer space. Again, the emergency room is going to be important, or I call it the space-rated emergency room. And then something called in situ resource utilization. This is a prototype that is being built that looks at how can we take soil from, let's say, Moon, and convert it to water for the astronauts as well as fuel for spacecrafts. And understand that these systems are very complex. And I use the iceberg here as an example of the risk associated with these kind of projects. Because at the very top you can see, like, for example, the top of an iceberg, and this is what the engineers and scientists and researchers and all expect for the technology and the human and the behavior of that system to happen. But underneath this, the big problem of risk associated with safety. Did we miss something that we didn't think about? Technical risk. Is there something in the technology that we missed too that perhaps can cause a failure of the mission? Cost. These things get expensive. If they start getting too expensive, there's a possibility that they'll have to scale back capabilities. Well, if they scale back capabilities, it can affect safety, and it can affect the technical capabilities of the system, as well as schedule risk. It's going to slow things down. And that's why sometimes these complex missions take years to develop. The James Webb Telescope was something like 8 or 10 years behind schedule, just simply because there were a lot of things that they didn't think about as they were developing these systems. And of course, there's something called contract risk as well. Not as big issue, but still a problem in developing complex systems. For example, if NASA is depending on a commercial company to build a certain computer, but then that company can't build it, well, that's going to affect NASA's mission. So contract risks are always a problem too as well. And then I'm going to briefly go into what's called human systems integration. And this is what NASA has been very, very strong in the last few years in developing this capability. And if you look at that, there are 6 elements to human systems integration. One is human factors engineering, again, factoring human limitations. Look at the safety of the mission. Look at the safety of a computer system. If you have a computer system that is not designed properly, it could cause a shock, electric shock to the human. That's not good. And so you have to look at the safety of the mission. Is it easy to repair if it breaks down? That's the responsibility of maintainability and supportability. Operations is a huge concern with NASA. This is like, for example, mission control centers operating the mission from the ground of Earth. Training. Do we train the astronauts properly? To make sure that they meet the mission objectives. Okay, so training is very important. As part of training is using the technology for developing mock-ups of systems that they're going to use and see if there's any shortcomings of those systems. And then habitability. We want to make sure that these places that the astronauts are going to live in, are comfortable for the astronauts, and they have all the conveniences for the most part, all the conveniences of home. Obviously, they got to have breathing oxygen. That's going to be obviously critical, and also water, food, and things of that sort. So each one of these is they work with many people to make it the best they can in that area, and then they put everything together to make the whole system, including all these human systems integration parts, what we call maximize or optimize, to do the best system performance that is possible. And so the total system performance is not only how well the system works, but how well the humans can work with the system. You get those two together, and you're going to have an optimized system. All right, and then there's NASA Systems Engineering. This is from the NASA Systems Engineering Handbook. It's the methodical way of developing complex systems. And so first, we look at what do we need, what is needed for this mission, so we develop test plans, requirements, things of that sort. And then we start developing possibilities of systems that could solve the problem. And we look at each one of these possible systems, and we look at which one is going to meet the cost, schedule, and the technical requirements. And that's the left-hand side of this. They call it the V model of engineering. The left-hand side is what we call definition and design. What do we need? What are we going to need? This is the most critical part of a complex system. Once we've defined the solution and everybody's good with it, then we go into implementation and we start building the actual system, the software, the hardware, the actual computer components, and we start putting everything together, and then we start testing all this. We start doing what we call environmental testing, like, for example, temperature, vibration, let's see, what's the other one? The vacuum of space testing. And then, we put this all together and start integrating it into the final destination, which in this case would be, for example, the Orion spacecraft. And then continuously, we're always looking at risk. This is just a big thing. We're always looking at risk. What if this fails? What if that fails? One of the big things I have to say about engineering that I came to learn in my career was always asking questions. What if? What if this happens? What if that happens? What if this goes wrong? What do we do here? What do we do, if this doesn't happen? You have to ask those questions, and that's the only way you can figure out if you have holes in your system. And I'll say a little bit more about holes in your system later. As we get further into more complex systems, this is called digital transformation. And I'm not going to get into too much the details of this, but basically, there's basically there's 5 things that we're starting to look at to deal with more complex systems. One is, first of all, what are our goals? What are our goals? Working with many different countries, working in to develop complex systems. And so, we have to look at how we're going to transform the experience of our workforce into dealing with, our partners, our multi-center partners, in transforming what we're doing now into something that's more what we call the big picture, holistic of developing complex systems working with many different countries. And we look at, what are the best practices? What's the best tools to use? What's the best processes to use? Which ones work, which ones don't work. And then we look at technologies like artificial intelligence, Internet of Things, mixed reality, automation, and things of these sort for technologies that's going to help develop these complex systems. And of course, the outcome is more complex systems, more ways of being more effective and reducing costs of future missions, but also attract and retain workforce and basically serve as a way to help students one day come work for space exploration, whether it's NASA, ISRO, or other countries. And so that's the digital transformation is a new way of trying to, let's say, optimize and make better the processes that we currently have in place to make them even better for these future missions. Are going to be even more complex than things like the space station. So you have the goals, the targets, the levels, the technology, and the mission outcome. So here's an example of all this technology and all this engineering of why it's important for NASA. A person by the name of James Reason back in 1990 came up with a human error. He called it the Swiss cheese model. And he said that that each design of a system, to try to minimize any hazards, you have to look at what are the barriers to prevent a problem to occur. You have the culture, the organization, you got requirements, you got design, you got safety, you got training, maintenance, and the crew health. And each one of these barriers help prevent some hazard from getting through the system. Here's an example of a hazard that's been deflected by saying, oh my gosh, we didn't have a requirement for this. And so they found it and they were able to discover a possible error. This one here deflected in design. They said, oh my gosh, we overlooked this in the design. And it's a good thing we caught it early on. But humans are not perfect, and we have basically issues with holes in the system. So the holes are things that we didn't see, and they got through. And so in a certain period of time, there's a hazard that got through the organization, they got through the requirements review, they got through the design reviews, they got through safety reviews, they got through training, they got through maintenance, they got through the crew operating the system, and an accident occurs. And that's the whole aspect of the human error by James Reason. So it's a way to explain how a system can cause, it is not just one thing that causes the accident. There's many things that cause an accident. And that's something to keep in mind too as well, that NASA does quite well, I have to say. We're not perfect, but we try to do the best we can. And so, if one day we're going to live and work on another planet, we're going to go and settle other worlds, like, for example, Mars, and onto other, let's say, planetary bodies. And then one day onto other solar systems, and perhaps one day other galaxies. So with that, that concludes my presentation. And let's see if I can stop sharing here.
That was amazing, sir.
All right.
I think I have had 2 months of learning dose in this last 20-25 minutes, and so much of information and almost 7-8 pages of notes I have taken while going through your extremely insightful presentation.
Thank you.
Thank you so much, sir. I think, sir, few of the things which I personally liked in this whole the technicalities of human space flight missions is, one thing that you mentioned is when engineering institutions or schools, for that matter, when they are focusing on STEM fields, the element of human is extremely important. So because this all the technology, hardware, software has to be eventually utilized by a human. So that's very important. I am, sir, just for just to give you a quick update from my desk. I'm writing a paper on steamer-based education system, wherein the STEM gets added with energy and resilience as well. So resilience is that human element which is required to carry on with all the hardware and software available around. So I think that was a real good takeaway for me personally.
Oh, good, good. Glad to hear that.